Hello, grade 11 chemistry students. This is a flipped lesson on metallic bonding, and with this flipped lesson, we will have completed all the topics in topic 4, which is bonding and intermolecular forces. So this is the very last topic, and this is a core topic, so this is for all students. So let's get into this. Here is the periodic table of the elements. And it's color-coded. All the yellow elements are metals, right? Metals, you can see that here. Whoops, here. All the green elements are nonmetals. We learned at the beginning of the bonding unit about ionic bonding between a metal and a nonmetal, right? Loss of electrons, positive ions called cations, gain of electrons, negative ions called anions. And then, of course, we have these very special elements here. The metalloids have properties of both metals and nonmetals, silicon, semiconductor industry, right? But again, the vast majority of elements known to humanity, right, in the universe are metals. And they look like this. Metals look like this. Here's some iron, here's a block of aluminum, here's some brass, here's some steel, here's some copper, right? Here's some other metals. And we have copper, we have lead, we have tin, we have nickel, steel, zinc. And what you notice is that there are all sorts of different shapes, right? We can have solid cubes, we can have cylinders, we can have wire, we can have spheres, we can have tubes. But what's common to all of these depictions of metals? What's common to all of them? They're all what? They're all solids. They're all solids, right? The vast majority of metals are solids. Not all metals, but the vast majority. Right, because here, of course, we have the only metal that's a liquid under standard conditions of temperature and pressure. This, of course, is metallic mercury. So most metals are solids. And so what does that mean for us? Well, let's ask this question here. Let's ask this question, right? Which of these states of matter is associated with the greatest forces, bonding or intermolecular forces? Which of these gases, liquids, solids, or plasmas is associated with the greatest forces and the greatest degree of order? Okay, of course the answer is solids are, right? The reason a substance is in its solid form is because there are forces acting between the particles of that solid, right, that stabilize that solid, and those forces must be overcome by adding heat energy to melt that solid to the liquid state, and then the liquid state to the vapor or gas state. So the fact that most metals are solids, right, the fact that most metals are solids, and the fact that solids are associated with the greatest forces must mean that there are significant forces acting within solid metals that make them solid, that stabilize their solid state. Well, what are those forces? Those forces are called metallic bonding. Those are metallic bonding, right? So what are the forces in a metallic solid? Here again, we have a variety of other uses of metals, forms of metals and uses of metals. All right. But let's go straight here to this screen here. Okay. And this is the bonding model for metals. And it's called the sea of electrons model. And you'll see why in a moment. It's also called the delocalized model. And it looks like IB prefers the delocalized model, but you'll see also why it's called the sea of electrons model. This is a depiction, this is, say, a cross-section of a a piece of solid sodium metal and a cross-section of a piece of solid magnesium metal, right? Imagine that you had a piece of metal that looked like this, and you took a slice of it, right? A very thin slice, and then you examine that slice under a very, very powerful microscope. You would see something like this. You would see that the sodium atoms are no longer atoms but ions. They're +1 ions or cations, and that the one valence electron of sodium, sodium's 3s1 electron, right, is free to move throughout these many positive sodium cations. If you were to do the same thing with a piece of magnesium and take a slice and look at that with a very powerful microscope, you would see an array, a regular array. We call that a lattice, if you remember, right? A regular array or a lattice of 2+ cations, magnesium cations, right, permeated by this sea of mobile valence electrons. In the case of magnesium, which is the element after sodium, right, 3s2 are the valence electrons, so there's 2 valence electrons per 2+ cation. Everything is electrically neutral, but the electrons are free to move through this solid space. There's empty space, right? Empty space, not occupied by the ions that the electrons are free to move through. And so the idea is that no one electron is associated with any particular ion. They are free to move through these ions. That's why we call this the sea of electrons model. We'll come back to these very different melting points in a moment. All right, but I will tell you that this model explains a lot. It's a very powerful model, right? This explains why metals are ductile, right? They may be drawn into wires, copper wire. You've all seen copper wire, okay? They're malleable. You can hammer them into different shapes. You saw the different shapes of metals here, right? All these different shapes of metals. Very versatile. Okay, you can't do that with ionic solids, right? What if you were to take salt and apply a great deal of force to it? Well, what you would do is you'd get crushed salt. You get salt powder. So ionic solids are brittle. They're brittle and they break when you apply force. But metallic solids, when you apply force, they bend. They bend, they give, they're ductile. And this sea of electrons model that we just introduced back here, can explain that. Because if you think about it, right, if you apply force to, say, a certain portion of a solid sample of a metal, right, what happens is that this row of ions can simply slide over to the right, and you haven't really disturbed the energetics of the system because the electrons are not associated with any particular ion anyway. And so the electrons don't care whether these ions are shifted to the right or shifted to the left, right, because they are permeating this space. But take a look at what happens if you apply force to, say, a sodium chloride crystal. If you apply force to a sodium chloride crystal, and if you shift these ions to the right, then the pluses start to repel each other, and the negatives start to repel each other, and the energetics are now unfavorable. So that's why applying force to an ionic solid causes it to split or break and not bend. All right, so it's very interesting. This is what scientists do. They develop simple models that explain a lot of observable phenomena, right? And if we go back to this table here, metals are good conductors of electricity, good conductors of heat. We know that. That's kind of what we're seeing here as well. All right, there's water boiling in a copper pot, right? Good thermal conductors, good electrical conductors. This is an electric motor. And what we're saying is that this delocalized sea of electrons model can explain all of these properties, right? Well, we talked about these two over here and why you're able to do that with metallic solids but not with ionic solids. Well, ionic solids are not good conductors of electricity or heat, but metallic solids are. Metallic solids are good conductors of electricity because, again, these electrons are, free to move in response to, say, an electric potential, right? Because of the nature of this bonding model. If we look at, sorry about that, metals are also good conductors of heat. Again, for similar reasons. So the point is that this simple delocalized sea of electrons model can explain a lot of the different properties that we observe for metals that are unique to metals. Now let's look at these two different melting points, and your homework assignment is to come up with as many reasons as you can why sodium has a melting point which is so much lower than magnesium, right? Magnesium is right next door to sodium in the periodic table. Periodic table all the way back here, all the way back here. There's sodium, there's magnesium. So it's right next door. Okay. And what you're going to do is you're going to discuss amongst yourselves at your tables. You can do this with your friends at your tables, and you're going to come up with as many supportable reasons to explain the greater melting point of magnesium versus sodium based on what you now know about this model and also based on what you know about the properties of these two elements. Let's see what you come up with, right? And I'm going to post that task in ManageBack. You guys are going to complete that task this evening. All right? All right. Oh, we looked at this already. So there's really not much to this topic. Well, actually, I shouldn't say that. There's a lot. You know, you could spend your life studying properties of metals and metallic bonding. But in terms of the IB curriculum, there's not much to this. In fact, we're about to be done with it. The only other thing we need to mention are alloys. What is an alloy? Well, an alloy is a mixture of metals. It's a solid mixture of metals. It's a solid homogeneous mixture where the metals have been combined in the molten state and then allowed to solidify so that there's a regular distribution of metals of element 1, right, or metal atoms of element 1 with metal atoms of element 2. The sea of electrons model still applies, right? So alloys are things that you know. Bronze is an alloy, is a combination of copper, the two metallic elements, copper and tin. Brass is a combination of copper and zinc. Steel, right? Where would the world be without steel? Right? Steel is a combination of iron with originally carbon steel to make swords and knives, right? Which was vastly superior to just plain iron. But of course, these days we have all sorts of different steel. So this is all iron combined with nickel or chromium or manganese or tungsten or vanadium or molybdenum, right? And the idea here is that by substituting, say, one iron atom for a chromium atom or a vanadium atom, right? By substituting one metallic element for another, you change the properties of the original substance. So in the case of adding carbon to iron, it was discovered a long time ago that swords made from high carbon steel lasted longer, didn't rust as fast, You could sharpen them to a much sharper edge. They were vastly superior, so it improves the properties. In general, it makes the metal harder, right? And this graphic from your textbook shows that, because now it's more difficult to push these atoms to the right. They don't slide quite as nicely because of the presence of this different atom in the alloy, right? You don't need to know these dates. These are here just for history, right? The Bronze Age, you studied this in INS, the Bronze Age, right? 2500 BC, the Brass Age, the Steel Age, the Iron Ages, somewhere in here, right? Somewhere in here. But we don't need to know these dates. They're just there for interest, okay? That's it. That's all there is to metals, metallic bonding, all right? So study this, play it again, make your notes. We'll practice some of these concepts. And that takes care. Congratulations, everybody. Congratulations. That takes care of topic 4, bonding and intermolecular forces. Of course, the HL students had their own special topics. There were 2 special topics. Hybridization is the second one we just completed, and the first one was a more in-depth look at Vesper, right, for the AX5 and AX6 geometries, and as well as related aspects of that. All right, but that's it for topic 4. You will have a unit summative test on all of topic 4. Paper 1 on Friday. All right, so that's posted in ManageBack, but I will tell you that right now so you can begin to prepare for that. That's all for now. Have a wonderful Tuesday, and I will speak with you guys tomorrow, Wednesday. We'll do a Skype session so I can take a bunch of your questions, of course, before you take that summative test. All right, take care.